Chapter 11, Lecture 1, Heat Exchangers. Heat exchangers are devices that facilitate the exchange of heat between two fluids that are at different temperatures. They are commonly used in practice in a wide range of applications, from heating and air conditioning systems in a household to chemical processing and power production in large plants. Heat exchangers differ from mixing chambers in that they do not allow the two fluids involved to mix. The simplest type of heat exchanger consists of two concentric pipes of different diameters called a double pipe heat exchanger. One fluid in the double pipe heat exchanger flows through the smaller tube, while the other fluid flows through the angular space between the two tubes. They can fairly be classified as by how they flow. They can have parallel flow, where both of them flow in on the same end and flow out on the other end. And they can be counterflow, where they come in on different ends. For example, the hot fluid comes in on one side and the cold fluid comes in on the other side, and vice versa. They go out on the other sides. The cold comes out where the hot goes in, and the hot comes out where the cold comes in. Another type of heat exchanger, which is specifically designed to realize a large heat transfer surface area per unit volume, is known as the compact heat exchanger. The ratio of the heat transfer surface area of a heat exchanger to its volume is called the area density, beta. A heat transfer with a beta greater than 700 is classified as being compact. Examples of compact heat exchangers are car radiators, glass ceramic, gas turbine heat exchangers, and the human lung. Another example of a compact heat exchanger widely used in industrial applications such as chemical processing, fuel processing, waste heat recovery, and refrigeration is the printed circuit heat exchanger, referred to as the PCHE, shown below. In compact heat exchangers, the two fluids usually move perpendicular to each other, and such flow configuration is called cross-flow. The flow is further classified as unmixed or mixed depending on the flow configuration. So in slide A, we have both fluids are unmixed. The baffles kind of separate the cross flow. In slide B, we have what's known as one fluid mixed, one fluid unmixed. Perhaps the most common type of heat exchanger in industrial applications is the shell and tube heat exchanger. These are the ones that our submarine had, for example. Heat transfer takes place as one fluid moves inside the tubes, while the other fluid flows outside the tubes through the shell. Baffles are commonly placed in the shell to force the shell side fluid to flow across the shell to enhance heat transfer and maintain uniform spacing between the tubes. Obviously, despite their widespread use, shell and tube type heat exchangers are very heavy and therefore not suitable for automobile or aircraft applications. So in the slide shown below, what you would have in our typical submarine is that you would have water flow flowing in through the inside and then flowing across the tubes this way and then flowing out. Then you would have steam flowing inside the tubes, flowing down, and the baffles would sort of force this fluid to flow in and around and about, and then flow out to the shell outlet. Shell and tube type heat exchanger are further classified according to the number of shell and tube passes involved. Heat exchangers in which all the tubes make one U-turn in the shell are called one shell pass, two tube passes heat exchangers, as shown in figure A. Likewise, a heat exchanger that involves two passes in the shell and four passes in the tube is called a two shell pass, four tube pass heat exchanger, as shown in slide B. An innovative type heat exchanger that is found widespread use is the plate and frame heat exchanger, which consists of a series of plates and corrugated flat row passages. The hot and cold fluids flow in alternate directions, resulting in a very effective heat transfer. So as we've seen, a heat exchanger typically involves two flowing fluids separated by a solid wall. Heat is first transferred from the hot fluid to the wall by convection, through the wall by conduction, and from the wall to the cold fluid again by convection. Any radiation effects are usually included in the convection heat transfer coefficients. The thermal resistance network associated with this heat transfer process involves two convection resistances and one conduction resistance, as shown in the figure. So here we've seen this from their previous work in the chapters, I think it's chapter 3, how to set up these resistance networks. If we let the subscripts I and O represent the inner and outer surfaces of the inner tube, the thermal resistance of the tube wall is given by the following equation. Here, DO and DI represent the inner and outer diameters. K is the thermal conductivity of the wall, and L is the length of the tube. Then the total thermal resistance becomes the following equation. The area AI is the area of the inner surface of the wall that separates the two fluids, and AO is the area of the outer surface of the wall. So here you can see in the little figure how to calculate each one of those values. It is convenient to combine all the thermal resistances in the path of heat flow from the hot fluid to the cold fluid into a single resistance value R, and to express the rate of heat transfer between the two fluids as shown in the following equation. In this equation, U is the overall heat transfer coefficient, whose unit is given as watts per square meter Kelvin. And this is identical to the unit of the ordinary convection coefficient H. Here we can cancel out the delta T's, and this reduces to the following equation. And we'll use this equation in an example, and I'll show you how these work later. It's good to know that when the wall thickness of the tube is small and the thermal conductivity of the tube material is high, which is usually the case, the thermal resistance of the tube is negligible, and the inner and outer surfaces of the tube are almost identical. Therefore, the heat transfer coefficient simplifies greatly to the following. Representative values of the overall heat transfer coefficient U are given in table 11.1. In this case, we can see that it's graphed as the type of heat exchanger and the value for the U, the overall heat transfer coefficient. The performance of heat exchangers usually deteriorates with time as a result of accumulation of deposits on heat transfer surfaces. This is what's known as fouling. The net effect of these accumulations on heat transfer is represented by the fouling factor, RF. These effects on fouling on the inner and outer surfaces can be accounted for by including them in the heat transfer coefficient equation we've shown below. So here you get two extra terms. You get a term for the inner surface and you get a term for the outer surface for the fouling coefficients. These fouling factors are given in table 11.2 for different fluids. Let's take a look at Chapter 11, Problem 16E. A tube in a heat exchanger has a 2-inch inner diameter and a 3-inch outer diameter. The thermal conductivity of the tube material is given as 0.5 BTUs per hour feet degrees Fahrenheit, while the inner surface heat transfer coefficient is 50 BTUs per hour feet squared Fahrenheit, and the outer surface heat transfer coefficient is 10 BTUs per hour feet squared degrees Fahrenheit. Determine the overall heat transfer coefficient based on the outer and inner surfaces. So here we can use the equation in the book that's given, that we developed, shown here. So what we want to determine for the outer surface is U0. So we can simply multiply through by A0 and determine our equation here. Based on that, we can solve for U0 and plug in the values for the inner and outer diameters we're given. We can calculate The outer heat transfer coefficient is 4.32 BTUs per hour, feet squared, degrees Fahrenheit. We can repeat this process for the inner surface and develop the following equations. We can then plug in the values given and calculate the inner surface, the overall heat transfer coefficient at 6.48 BTUs per hour, feet squared, degrees Fahrenheit.